So this is example 4, section 2.6, evaluating limits of absolute value functions. So what we're going to notice here right now is that we're trying to get the limit of this quadratic over an absolute value. The graph is shown to give you an idea of what's going on and how to calculate the limits visually. On the right of -2, we can see that the function is approaching the y value of -1. On the left, we can see that the function is approaching this coordinate, which the y value is at +1. So the y value here is at 1, and the y value here is at -1. So I know the limit as x approaches -2 does not exist because the limit from the right and the limit from the left of the functions are different. So how do I show it algebraically? Before you do that, you have to understand the definition of the absolute value of x plus 2. And you have to understand that the most basic absolute value is the absolute value of x. So if I add in 2, what I'm doing is I'm shifting that function 2 units to the left. So the vertex is -2, 0. Now that -2 is important because that's where the function starts to change. So the definition is it's going to equal a positive function and a negative function depending on the domain. It's positive if x is greater than or equal to -2, and it's less than if x is less than -2. So think about, again, this is a line. Think about it having a positive slope and a negative slope. And that's why at -2, you have that V shape. So let's go ahead and calculate it algebraically. So the first thing we're going to start off with is calculating the limit from the right. I'm going to factor my quadratic, but this is where it becomes important. I have to redefine this absolute value depending on my positive or negative right-hand limit. So because I'm choosing the positive, I have to make sure that I'm choosing where it's greater than -2. And we remember from our notes right here, it's greater than if it's a positive slope. So I'm going to put in a positive x plus 2. As soon as I do that, I see the factors cancel. Then I'm going to look at what's remaining, which is an x plus 1 over a positive 1. And then I can use substitution to solve for the limit. I'm going to substitute -2 in for x, and I'm going to get -1 as an answer. You don't have to worry about that positive right-hand limit because I've already defined it by choosing the positive slope. So now I'm going to do the exact same thing except choose the left-hand limit. The quadratic in the numerator will be the same. But this time, because it's a left-hand limit, I have to use the less than because I'm less than -2. So now I have a negative slope. Still cancels, but the difference is I am left with a x plus 1 over a -1 in the denominator. So now when I substitute in my -2, I get -2 plus 1, but it's divided by -1. And now I have a positive 1. So do you notice the limit from the left and right are different, which is exactly what we said on the graph. So our final statement should be the limit as x approaches -2 of my original function. So I'll write it all out. Does not exist. And you can even make the statement, I'm just going to erase this. You can even write the statement since the limit from the right does not equal the limit from the left. And then you're done.